Olá, estão todos bem-vindos. You're all welcome to the last lecture, unfortunately, of Riccardo, of our mini course. So we please, Riccardo, I'm sure that the last lecture will be very interesting as the other ones.
Okay. So thanks again. Thank you. And for the people online, as for the other times, if I write too small or you don't hear, just type it in the chat or speak up. So I rewrite or repeat. Okay, so we are talking about. Okay, that's a great start. Doesn't work. So I'm afraid that with this, it's not very visible, but I try to speak loud. Obrigado. So we talk about Turing patterns. We've seen classical Turing patterns on network, and then at the end of last lecture, we saw that when the network is non-diagonalizable, we may have cases in which an eigenvalue of the dispersion relation is in principle stable, but there are hidden contributions who are perturbation dependent, who might bring the system to stability. So today we will give a mathematical ground to this fact by speaking of non-normal. I hope that online you don't hear all this squeaking. Non-normal networks. So in general, non-normal matrices and an operator. So non-normal matrices and operator have been studied by Trefeten, and you in the papers in the Dropbox you will find the references of Trefeten, who is a numerical analyst in Oxford. And so what happened is that they were studying some fluid dynamics problems, and they were realizing experimentally that even though the theoretical Reynolds number was very high, the flow would be turbulent at low Reynolds numbers. And then Trefeten with colleagues, they published a paper in Science in the early 90s. They found that actually these operators were non-normal. And so non-normality, as you will see, basically makes an operator or a matrix more sensible to perturbation. Okay, this means that the attraction basin of the stable state becomes it shrinks. So of course, infinitesimal perturbation, they don't really bother, but then finite perturbation. So infinitesimal perturbations, they exist only in mathematics textbooks. In real life, perturbations are always finite. And so we lose equilibrium. And there are so many effects of non-normality, not only on fluid dynamics or Turing patterns. Now there's Lorena here, and together we are studying the effects of non-normality on quantum measurements. So really, it's a universal topic. So let's start with a definition. The theory has been developed for matrices and operators. Yes?
When you say that it makes the system more sensitive to perturbation with respect to the same network, that is...
Yes. Yeah. So let's say I will not go into details with this, but if we consider the perturbed spectrum or pseudo spectrum with the same perturbation, the pseudo spectrum of a non-normal matrix or operator is larger, and it's larger of even order of magnitudes. And so all the results are valid for matrices and operators. So that's why sometimes you have the sub instead of max because you consider. Obrigado. Yeah, thank you. It's better. So A, B matrix, but it works also for operator. And it also works for complex matrix. But since we work with networks, all matrices will be real. We say that A is normal if it commutes with its adjoints. And being real, we could just put the transpose. Okay, so this is the relation of normality. It doesn't tell us a lot, but geometrically, this means an alternative definition is that there exists an orthonormal basis. So it means that the set of eigenvectors of A is orthogonal. If a matrix is non-normal, so it's the opposite definition. So non-normal networks are networks whose adjacency matrix doesn't satisfy this relation, which is very easy to check. This doesn't mean that the network, so the matrix is non-diagonalizable. It can be diagonalizable, but through a non-orthogonal transformation. Okay, so we already seen non-normal networks last time, because defective networks, so networks that are not diagonalizable, they are non-normal. This is the simplest example. But also we saw that in certain cases when the network was non-balanced, and non-balanced networks are non-normal, in order to expand the perturbation, we needed to multiply by the left eigenvector or right eigenvector, because only there we have the relation of orthogonality that we don't have if the network is non-normal, because it doesn't have an orthogonal basis. Okay, so there are about 80 different definitions of non-normality or equivalent. So if you want to, if you like linear algebra, you can check them. But then at the end, for us, the most important is the non-orthogonality relation.
This question of mathematical matrices, like instead of normal matrices, does it have sort of known interesting distribution instead of matrix? Like, is it a dense set or a compact set, open? Like, do you know?
That I have no idea.
Like maybe that could be related to how it could well approximate certain networks by normal networks. That might be interesting. I don't know if that ever makes sense. I mean, how far off is a network from being normal? You know?
Okay, yeah.
How far off can make it from being normal? That I believe would be.
Yeah. So I have no idea from a more mathematical point of view, but then practically there are some measures of non-normality, and so in applications normality doesn't exist. Okay, it's impossible. Well, you really have to make a controlled experiment. So natural network, empirical network, because also artificial networks are all non-normal. But then, yeah, there are some who are strongly non-normal. And usually, as you'll see, there is sort of hierarchy that you cannot go back to the initial point, or you can go, but much more difficult. Those who are have a low non-normality, they are basically normal. They are not mathematically normal. So it's like when you study synchronization, it's impossible to have full synchronization. Okay, but in applications, if you have a certain degree of synchronization, you say that the system is synchronized. And the same is for non-normal networks. And yeah, when you ask questions, can you speak a bit louder, because your questions are very interesting and not always you can hear them in the. So we need to define two important things. Given a matrix A, we define alpha of A as the sub or the maximum, because it's a matrix, but then the classic definition, if you look in textbooks, is a spring of the real part of the spectrum of A. So it's the maximum real eigenvalue. Then we can define the Hermitian part.
Is the maximum real eigenvalue, or is the maximum the real part of the eigenvalue?
They coincide. No, sorry. In our applications, they coincide. I don't know if there are some cases in which there is a real eigenvalue who is smaller than, but no, I think that in general, no, they don't coincide. So it's, sorry, the maximum real part. Then when we deal with the Laplacian, they coincide because it's always zero. Okay, so H, no, sorry, I'm not good at multitasking. So the Hermitian part of A is equal to A plus A adjoint over 2. So if we put the transpose, it's the symmetric part. So basically you take a matrix and then you take only its symmetric part, because every matrix is the sum of a symmetric part and an anti-symmetric part. And anti-symmetric is with the minus, but we don't need it. And so we define omega of alpha as the sub of the spectrum of the Hermitian part. 3. Okay, we don't need the real part because Hermitian matrix has a real spectrum. These two quantities, alpha and omega, they are very important in the studying of non-normal dynamics. And alpha is called spectral abscissa. And omega numerical abscissa. Alpha gives us information about the asymptotic behavior in a dynamical system. Okay, the solution of a linear system. Now I will go into details. They converge at a rate given by the largest eigenvalue, the largest real part of the spectrum. Okay. What is very interesting is that omega gives us an idea of the short-term behavior of a system. And that's the key to non-normality. Okay, so
it seems so similar.
Yes, they're very different. Yes, because let's say that now you gave me the set for a definition. That it's an equivalent definition of non-normality. That
so for normal, they coincide.
Exactly. Yes, that A is non-normal if and only if omega is greater. So different than alpha. Well, no, it's always greater. So let's say I should have written that A is normal if and only if alpha is equal to omega. No, sorry. No. This is correct. The opposite, I'm not sure now, because there is a case of asymmetric matrix with that is normal. So no, this is A is not normal if and only if omega is greater than alpha. So I will erase, just leaving this on the bottom. Let's consider a linear system 2 times 2, so x dot equals ax with some initial conditions that are non-zero. Two times 2. And let's take A of the following form. So for example, -1, a certain coefficient A, small a, and then -2. Okay. And you will find this in the paper. I will cite it many times today. Aslani and Carletti, Physical Review E, 2018. Topological resilience of non-normal networks. That's the first paper in which non-normal networks are introduced. Okay, so this matrix is stable because the eigenvalues are -1 and -2. Okay, so the solutions, both solutions, they will decay with a rate proportional to -1. Okay, so if we plot the norm of the two solutions, here we are sure that we decay. The equilibrium solution is 0. So any perturbation, and then we go back to the equilibrium. Okay. However, if you integrate numerically the system for 2 values of A, now I'll give you the exact values that are on the paper. So, okay. In a case in which A is 1, you will have this. So this is x0. This is with A equal 1. But now, if A equal 10, we observe a transient growth before decay. This is for A equal 10. Okay. So the matrix is stable. Looking at the spectrum, we do not see this coming. And in applications, this can have dramatic consequences because, well, nature is not linear. So this might be the local stability. So linear system, okay, it goes back to the equilibrium. But if it's non-linear, the Hartmann-Grobman theorem is valid only in a neighborhood of the equilibrium point. So once you leave this neighborhood, you don't know what happens. So in applications, this has catastrophic, can have catastrophic consequences. What we see is that what we can compute is that omega of A with A equal 10 is positive, while omega of A with A equal 1 is negative. And the two alphas, I will go here, but then so alpha of A is equal to 1 independently for any value of small a. Okay. And before that, all this non-normality came out in the context of fluid dynamics, ecologists were studying this omega, and they were calling reactivity of the system, because it's how the system reacts to a perturbation. There are systems who are not reactive, but systems who are very reactive.
It's one, no, another one. Alpha is one.
Alpha, sorry, thank you. Alpha is negative, -1, thank you. Yeah, alpha is, depends only on the diagonal, because the matrix is triangular. So it's similar to a diagonal matrix.
This is why it's the long-term period.
Yes, yeah, exactly. So alpha lives here, let's say, tells you what happens here. But then in applications, you need to know what happens here. Because usually the asymptotic behavior, you don't really care, because it's not interesting for a linear system. You see Turing instability, you have local asymptotic divergence. But then, of course, nonlinearities, they enter in the picture, and so they stabilize the system in a path. Okay, so I will erase, delete. Yeah, I think for 2.5 videos I've said delete. So yeah, when I run for president, you can blackmail me with. So I will now prove that omega actually is related to the short-term behavior of the system. And again, this is found here, but this is not a new result, but I think this is a very good start if you want to study non-normality. So let's compute the sum for the solution with non-zero initial conditions of this quantity. At t equals 0. So this gives you, normalized by the norm, gives you what happens to the derivative of the norm for t 0. Okay. Yeah, for t equals 0. So it should be 0 plus, because you go from the right to the left. So we can, every time is taken for granted. So okay, the sum of non-zero norm, non-zero initial conditions, and then we can write this as the product, scalar product solution. So definition of the norm, and always at t equals 0.
Right there, they're divided by 0 as well. Like 1 over x or 1 over x0, absolute value.
No, it's the initial condition overall.
No, this is, you haven't computed. Yeah, you're right. So this is for these two.
Okay.
So then at the end, yeah, it's true. At the end, you first you do the calculations, and then so here is so then we proceed with the derivative. So this is equivalent to the scalar product of x transpose with dx dt plus dx dt transposed, scalar product of x. But then we take another norm, so squared. This is the derivative of the square root, and still t equals 0. Sorry about that. I hope that's online. You can see, maybe yes. T equals 0. But this is the matrix times X. Okay, so again, supreme with non-zero initial conditions, and then we have X here, A. Then 1X goes away with the norm. Here is X transposed. Sorry, A transpose. Sorry, only one scalar product. And here, 2 X, norm of X. And of course, I forgot the vector for every norm. Okay. But now what is this? I defined it with the adjoint, but then it's real, so it's the same thing. It's the Hermitian part of A. And now I can calculate with in t equals 0. And so I have finally sub of x0 non-zero. And then we have x0 transposed, Hermitian part of A, scalar x0. I think I need some. Oh, no, okay. It's the norm, so x0 scalar x 0. Okay, we get to this. And now we use the Rayleigh principle.
Isn't there a square root of X?
Yeah, I might have missed a square somewhere. But then, okay, yeah, you can check it.
Yeah, you put the square over there, up there, but not below there.
Yeah. Maybe I missed it here. Yeah, thank you. Thanks. But this.
No, but it's one open, no? There's a half, so it's okay. No, you're right. It's square.
Okay. So here, this for the Rayleigh principle. So I will erase in the middle so that we keep the important part, the beginning and the end. Right? Who cares what's in the middle? If only we could say that at exams, right? The beginning is correct, the end is correct. So for any non-zero vector, we have that lambda max of a certain matrix is equal to the sub of a non-zero vector transpose A and then B transpose scalar B. This is equivalent to the maximum eigenvalue. Okay, and which is so the maximum eigenvalue of this is omega. By definition, is the maximum eigenvalue of the Hermitian part of A. And so you see that omega gives us the behavior on short term. Is the slope?
Sorry, stupid question. There you called the property you called Rayleigh something.
Rayleigh principle. I don't remember the spelling, so I will, assuming that I wrote it correctly. This is Rayleigh principle.
Sorry for my lessons of linear algebra.
I don't think I did this in linear algebra. I learned it when I studied this. Okay, so let's try to give a meaning to this transient growth and correlate it to the actual solutions of the system. So I will erase. Let's go back to our simple system. X. Yeah, thank you. It's a bit hot.
Just let maybe open the door for me. The air is pretty much only there's noise.
Yeah?
Yeah.
Yeah, okay. Yeah, that's true. No, maybe no, then it bothers the.
Let me see if I have
Okay,
With the door open, there was also
the noise.
people.
Yeah, okay. Let's suffer 20, 30 minutes more and then. So this transient growth that we see, it's easy to understand when the matrix is degenerate. So when the spectrum of A is only one eigenvalue, but then the eigenspace has dimension 1. So every matrix that is not multiple of the identity. The identity has the same eigenvalue, but 2 eigenspaces. So in this case, one solution, the first solution x1 is equal to E lambda t v1, where v1 is the only proper eigenvector of the matrix. And then the second solution is x2 equal to E lambda t v1. So here they are. Yeah, so here we have that no, it's the same. So the algebraic multiplicity is equal to the geometric multiplicity. And so, I mean, to generate the matrix, we need 2 eigenspace, so we need a generalized eigenvector. That in this case, it's easy to find. It's any V2 such that A minus lambda identity V2 is equal to V1. So now if here we study the norm, we see that for short t, we have actually an increase. So here we see why there is an increase. But then, if that's not the case, we can prove that actually, if the eigenvectors are not orthogonal, there is an extreme, so a maximum, a point in which the derivative of the norm is 0. And this gives us the geometric property. Now, do I have time to do this calculation? Maybe not. But then, so you can, I will give you a trace. So if you have a matrix so the spectrum of A is equal to lambda 1, lambda 2. You can write the 2 solutions. Lambda 1, t, t1. And of course, before I forgot the constants given by the initial conditions. And then it's 2. T lambda 2, t2. And then if you compute the norm, the derivative of the norm, of the solution, you see that you can have a zero only if V1 scalar V2 is non-zero. Okay, so the matrix needs to be non-normal. If the matrix is normal, then you can never have a change in the growth of the node. Okay.
There's a reason why the ICT will go to zero.
It goes to zero, but then if you study the derivative over t from 0 to infinity, you find that if these two, it can have zero, so an extreme, a critical point, only if this is true. So it's not that simple. The implication is not true. And this was studied in detail in a paper by Motter on chemical reactions, where in the appendix they focus on because this is the trivial case, but there are some exceptions. Okay, so all this now, yeah.
So this is the second case. We have two eigenvalues.
Yes.
We have two Canadian vectors.
Yes.
And then in the other case, if you have the degenerate case, you always have a maximum. And in this
Yes.
case, you only have
So the other case, so when A is non-normal and omega is positive, you have this transient
when
growth.
you have just one eigenvalue.
Yes, when you have an eigenvalue, this is always true, and it's also easy to see from the solution. When with a generic case, it's not you wouldn't really see this behavior. Where does this growth come from? And so if you do the computation, you see that there can be a zero if the two vectors are non-orthogonal.
This will be the example of Timoteo.
And Malgor in the paper, yes. I don't know if they made this calculation, but it's really a
Changing
simple
the
one.
A with the one case to the other.
Yeah. So all this can relate to Turing instability in a way you can guess, meaning that if the network is non-normal, we have a transient growth, but then the system is nonlinear and we go unstable, as we saw a little bit last time. But there is a much deeper result that relates non-normality of the isolated system, so of the model, of the reaction, Losca Volterra, Brusselletto, Tsunagumo, whatever. It relates it with the non-normality of the linearized Jacobian, which tells us that the relation between the two species to have Turing instability has to have some kind of asymmetry. So again, this equation that you've seen by now many times. And then it will be the same. So the two reaction diffusion equations. Linearizing, we would arrive, this is on continuum support, on JK that was equal to the Jacobian of the linearized system, and then minus K squared and the matrix of the diffusion coefficients. Now, we can compute Okay, so if we look at the spectrum, we know that sigma, so alpha of J0 is negative because we have homogeneous equilibrium. And we can compute then H of JK, so the Jacobian part, Hermitian part of the global Jacobian, and this will be Fu minus K squared du, and then Gu minus or plus Fv squared, then the same here, Gu plus Fv squared, and then Gv minus K squared du. So we take this matrix and we take its symmetric part. So to have Turing instability, we would need alpha JK be positive, so that the linear stability, the stability of the linearized system is unstable. Now, huh? B? Ah, yes. And so, of course, if this condition is not met, we don't have Turing instability. Now, let us assume that omega J0 is also negative. So it means that the linearized system does not have a transient dynamics. Now, with the same, with a similar calculation, so this, we write it here because we need it. JK is equal to J0 minus K squared E. This, okay, you've seen it. So with a similar calculation, if we compute the norm of the perturbation that I wrote as ZK, we arrive, it's a similar procedure to before, and then I will also scan the nodes. So all the parts I skipped, you find them here. We arrive to this with the Hermitian part ZK, and then ZK transport ZK, normal ZK. And now again, for the Rayleigh principle, you know that this is the JK. Yes. This is necessarily less because this is the upper bound, is the maximum eigenvalue of JK. And here, sorry, was JK. So the Jacobian with space. Okay, so we have that at the end, the norm of the perturbation is bounded so Here there is a K. So this part is bounded by omega. So this is bounded by omega. And so we see what's obvious, that if omega jk is negative, the perturbation doesn't grow because the derivative is negative. So there is an upper bound of the growth of the perturbation. And now what I think is the most interesting part is that, so we assumed now that also omega J0 is negative. But we know that omega Jk is equal to omega H Jk is equal to H, so the Hermitian part of J0 minus Hermitian part of the matrix K squared. Well, K squared I can bring it outside. D. So we have assumed that its maximum is negative. Here, the maximum is of course negative. Minus K squared D. Because it's a diagonal matrix with minus K squared D U minus K squared dB. And so from a theorem that, yeah, I would have liked to give you the whole formal, but it's like one page of enunciation, but then it's White's theorem. It tells us that if this is negative and this is negative, then also the maximum. So omega, yeah, I don't have to write the maximum every time, of Jk would be negative. And so we cannot, if we want to have Turing instability, and we have that alpha J0 is negative necessarily, we must have as a necessary but not sufficient condition that omega J0 is positive. So it means that J0 has to be non-normal and with the spectral abscissa, so the numerical abscissa, so the reactivity positive. And this gives us an idea of the mechanism. You have this asymmetry, not only the diffusion as it was taught. This result is from the early 2000s by Newbert, Caswell, and Murray. So two ecologists and one mathematical biologist. And they realized that, yeah, we need this asymmetry in the diffusion, but then at the end, we need the asymmetry also in the reaction. And I think that this is really a cool result. And then if you check the paper with all the formal proof is really nice. Okay. And now we can conclude the last part. Going back to non-normal networks.
Which year?
2002, yeah, sorry. Mathematical biosciences is the, and then I don't remember if I put all the references like this one, I think no. but then you can write me and I will send it to you. Or you find it for sure in the papers that I put there, because we always cite this. This is a milestone in the study of non-normality. So for me, learning about non-normality from zero is the paper of Treften on hydrodynamics. That's a Science of 1993. Then there is this paper, and then Aslani Carletti. Those are the three, I think, most important paper if you want to study Turing instability on non-normal networks, to understand a bit what happens. Okay, so we are getting to our favorite part, which is the end. So in Turing, again, and this is promised the last time I'm writing this, but now it's on a discrete support, so on a network. G, I, L, I, J. Okay, so we have an asymmetry in this part. So the reaction part is non-normal. And that's necessary to have Turing instability. We cannot have it if we don't have this asymmetry. So the logical thing to do is, what if we also put non-normality here? You already have a transient dynamics. And so this was done by Margot and Theo. And just to give you an intuitive idea of how non-normal networks work, we take a system of one species. So
The non-normality refers to the first part.
So the first part is we have it, non-normal. Now the support that we used was continuum, was a symmetric network, or also a directed network. And now you will see at the end that this is not, it's a particular, when it's balanced, it's still normal. What if we make the Laplacian non-normal? So actually, at the end of last time, a defective network, non-diagonalizable, is non-normal. We have the same effect. But how do we build, in principle, a non-normal network? So imagine a system that has a diffusion and a decay. The example that Margot and Theo do is to have animals diffusing in a circle. Let's take a circle. And there is some poison. It's a bit cruel, but then no animal has been hurt during this thought experiment. So they diffuse, and some of them die. Okay. If we study the norm of the solution, assuming that they diffuse faster than they decay, so that we see diffusion. Okay, otherwise, we don't see anything. They die right away. The poison is not that strong. If we study the norm, then we have that all the solutions starting from a random initial condition, they will eventually, so this is a linear system. Diffusion is linear, reaction is linear. All the solutions go to zero monotonically. Now, if you don't see them monotonically, it's because my drawing skills are not that good. But then they are. And so we don't have any transient. And in fact, a network like this satisfies this relation. It's called a circulant network. And these are the only network that are directed but normal. And already by the definition, you see that this is recurrence. You go back to the starting point easily. And then also the network studied by Malgor in the Nature of Communication, at the end they also were circulant. This we understood it after. Because there was a constant flow of the topology from a point to the big, a circular recurrence. What if now we cut one link? So we have a chain with a start and an end. So already we see this relation of hierarchy. And by the way, this network is non-degenerate. It is degenerate. So it's non-diagonalizable. Now, if we let's study what happens in all the nodes but the last one. Okay, we have a monotonic thank you, decay, maybe even steeper, because yeah, once you leave a node you never go back. What happens in the last one?
Accumulate some of the others, but eventually it's going to die as well because of the evaporation.
Yeah, exactly. So you will accumulate, but then the system is linear. And so then at the end you decay. And then the norm will at a certain point follow only the first node, the last node. Okay. So this is exactly the idea behind non-normal networks and the effect on the dynamics. If you have a strong directionality, a strong hierarchy, the network is non-normal. This is the intuitive idea. Now, if you have a non-normal network with a non-linear reaction, you accumulate on some nodes, but this gives you the push to leave the attraction basin of the stable state and move towards an unstable state. And so, if you have your dispersion relation, and you are negative, and even if your directed eigenvalues, they are negative, with finite perturbations, you are unstable. And so looking at the dispersion relation in the complex plane, the one I showed you last time, you have your spectrum here. But then you somehow enter the instability region with the perturbed spectrum, the pseudo spectrum. This is not the whole story. The fact that the perturbed spectrum enters the instability region is necessary but not sufficient, because that's still an open question, and we have many open questions. So you're welcome to work on that.
Answer the question.
Yeah. No, well, if you answer all the questions right away, there is no fun. Because, for example, there are some measures of non-normality that we are using with Lorena for quantum weak measurements. So one is omega minus alpha, gives you a degree of non-normality. Another is called one Enrichi, departures from non-normality. Departures. There are many different measures, and we actually a priori, and now probably it will be clear what I said last time. once you have a certain setting, it's perturbation dependent. It depends which modes you are exciting. And this is at least my opinion. It depends which eigendirection you are hitting. There are some good ones, because if you imagine an n-dimensional attraction basin, you will have a shrinking of the attraction basin, but not every direction will shrink at the same time. So if you hit a direction who shrink a lot, you exit. And in the paper that we did, Journal of Theoretical Biology, 2019, we made a figure that was made by Theo. And actually, that's a figure that with Professor Stefanella, we chose to represent the mini course. That if you imagine your attraction basin as a potential landscape, it's the easiest way to see. So maybe you are here, and you are in this direction. You go in this direction up here. Let me draw it higher. You go in this direction. That's your linear stability analysis. But then due to non-normality, it's like that you jump higher. And so if looking for the last time at the triangle of the Brussellator, you have one increase due to the directionality, but this is still Turing instability, because here your discrete dispersion relation is positive. So still you lose your equilibrium. But then you also have an extra area which strongly depends on the network, is very numerical. And that's not anymore Turing instability, because after your analysis,
Like for what value? How does this jump occur that way?
that's a good question.
For what value does jump occur?
It depends on the network, it depends on the model, it depends on the perturbation.
At a minimum value, with the time switch, don't achieve it, won't jump.
Yeah.
From that one.
So if you take, for example, a perturbation of 16 order of magnitudes less, it's unlikely that you. What we do?
Reminds me of mainly by the drawing you point me of that tunneling, quantum tunneling.
Yeah, it's so yeah. At the end, it's not related to quantum tunneling.
Yeah, of course.
But then, this probability is not a quantum probability, but it's a probability which direction you need. If you find what we do here for each value of the parameter, we perform a simulation a certain number of times with different perturbations. And then we say, for example, if it's always unstable, then it means that you are so close to the equilibrium, or it's such a network such that, and a setting such that you are always be unstable. But then in some cases, you are unstable 1/50 times. But then if you save that perturbation and use the same perturbation, it's deterministic, so it's not stochastic. One interesting thing would be to study stochastic patterns. So they did it in the US at the Northwestern. Yes, there is a Professor Goldenfeld, and he studies stochastic patterns. And they did it, but on continuum, not on network. But then of network, already stochastic patterns, you increase the instability region. So with non-normality, you go much further. Okay, so before I conclude, of course, so one important thing of the normal network is that, maybe I already said it, I don't remember, but I wrote there to tell you that empirical networks are not normal. This I think I told you. And this is another paper by Malbor and Theo. And then Malbor found that an increase in non-normality means an emergence in the network structure of leader nodes. So of nodes who are either source or sink. So this really gives an idea on the hierarchy.
Sorry, nodes that are what?
That are either sinks or sources.
Okay.
So they only have outgoing links or incoming links. And so really non-normality is really connected to this hierarchy that there's in nature, but then they're also quite robust, the networks. So a chain is not stable. It's not a robust network, because you cut one link and it's already not anymore connected. And then also this fact that you cannot diagonalize, it means that somehow information cannot be decomposed. It's all entangled. And that's also what we are thinking of with quantum measurement. So last thing, so there are three things that in my head I wanted to do today. Then of course I will not. But then there are the papers in the Dropbox. So the first thing, I will just give you a hint, is about synchronization. Now you will have a mini course on synchronization, I think February, March, with Mattia Frasca and Valentina Gambuzza. They are two professors from Catania, world leading expert in synchronization. So they will define the mass stability function and properly. Also, there is a book by them that I think I gave you, the book on synchronization. So that's a good book to start. But then also, if you think about Turing instability and then the rest of the network, now here, in every node, you have a certain dynamical system, isolated. This could be a limit cycle, so an oscillating solution. Instead of a fixed point, now your homogeneous state is the state in which all the nodes oscillate together. They are identical dynamical systems. And there is a mechanism. So in the Brussels laser, so I told you it was the last time you saw the triangle, I lied, but that's the last time. So here the equilibrium of the homogeneous system was stable, and here unstable. This is a Hopf bifurcation. So it means that here there is an oscillating, a stable oscillating solution. So the fixed point becomes unstable, and then it appears a limit cycle. And so then there is a similar mechanism here of synchronization. And there is, you can, with diffusion, so with the difference of the two species, you can break the synchronization, can disrupt the synchronization. You have all your neurons synchronized together, and depending on how they are coupled, you can desynchronize or not. So this is the first thing. Sometimes it's called Hopf-Turing, but this takes really a meaning of synchronization if you go on networks. On continuum support, they call this, like crossing this bifurcation curve, Hopf-Turing. I don't really like this definition, also because I'm used to this. Then, especially for you theoretical mathematical physicists, we have relativistic pattern. Okay, now it's relativistic because you put an upper bound on the signal propagation, because with the diffusion equation, with fixed diffusion law of diffusion, if you perturb your domain with a delta, at t, as soon as t is greater than 0, you have signal in all the domain, in the whole domain. And this is a good approximation for a small domain. Okay, you can modify fixed equation with Catania's law of diffusion. And so there are some papers in the Dropbox. You can check the literature if you are interested. What you get is a relaxation term and you get a second derivative. So your equation becomes from this form. And then again, the diffusion part. And the same for B. And you can solve it. And we can see that there are the same old diffusion-driven patterns, but then there are some new ones emerging from the inertia that are called inertia-driven patterns. And then last thing, the group in Florence, and then we extended it for asymmetric network, found that it's possible to study systems where there's no diffusion, B, I, B, J, and then something analogous for B, when there are the interactions that are non-local. So this is a function that just becomes small f when E is equal to J. And just by interacting without displacement of particles with species in the other nodes, we can rewrite the system in a similar way with small f plus L I J. That should be this, if I'm not mistaken, because I didn't think I would have time to actually get here. J, E, I, B, J. I think it's this. But what's important is that this is not the same Laplacian. It's called the reactive Laplacian, so it's different properties. But that's really cool because from this, you don't have diffusion, but you can go back to a system that you can study with the techniques developed. So these are just three directions. It's a really wide domain, and for Turing, also for non-normality, there are plenty of open questions. So I told you a story that, of course, it's affected from my experience, because I did my master thesis with Malbor and Theo while they were working on this. So of course, my vision of things are affected by that. But then this is the starting point for then if you're interested in the subject for some independent studies. And there are really applications in many domains, also in quantum systems. Nakao, the one from the paper on networks, they found Turing patterns on quantum system, something related to entanglement. So it's really a rich domain. So again, thank you to Professor Stefanella for organizing this, and thank you for your attention.
Question? Lorena is there.
Hi, yeah. No, I don't have, thank you very much for the lecture, was great. I just have a comment is that I think we should have a look a little bit better when our matrix, it's not necessarily real.
Yeah.
Because I think some things that are not defined in for real matrices could have sense for complex ones, or maybe some other parameters should be redefined. I don't know, but I think we should have a look there, because everything is defined for real matrices.
Yeah, that's true. That's true. Because even though you're right, even though the theory is general, then in all applications the matrices are have real coefficients. So that's true. And in quantum mechanics, we have the Pauli's matrix, so they are complex. Yeah. Thanks.
Thank you very much, and very interesting lecture.
Thank you.
Thank you, Lorena. Bye-bye.
Bye.
Bye-bye.
Bye.